Hello everybody, today we'll be covering traits for CS 128 honors. So the goals for today, first to review some generics from last time, and second to cover traits. So generics, they can represent any type in a declaration or function definition by using, for example, a capital T. This lets us combine type declaration for functions where the type isn't as much of a concern as long as it's consistent. Like for example here, for where it doesn't matter if it's an I32 or a character as long as it's the same throughout. That's what this capital T does for us. But sometimes a type doesn't know if it can be compared to another. For example, here it could be anything. Like, for example, if you put a string there and a string there, what defines what's greater than in a string? This is where traits come in. We can claim that T must implement a trait called partial order. We will discuss this right now. So first, generics and functions. We want to declare that they have a comparison behavior. One solution is to do like other languages, like C++ or Java, where you have a parent class that has an interface to a function, where all the subclasses use, like class dog and class cat, which both have make noise from their parent trait, from their parent class. But Rust takes a slightly different approach. Instead of this inheritance from the top, we can do it to where there's a trait called noise, where it defines make noise. And we implement noise for dog and we implement noise for cat differently. They both implement noise. They're not built from noise, but they both implement it in themselves. Then we can filter by structs that only accept this noise function, essentially. We can filter to make sure that the struct we're calling has noise implemented, which is earlier here. We can filter that the data type we're accessing has partial order implemented beforehand. So here, traits formally are defined as shared functionality that types can have. We can share this functionality by both implementing this trait on a struct. A trait, like such, contains a set of functions that types can and sometimes must implement. Like here, it must be implemented since we don't provide a default implementation. Here, instead of writing, for example, summary, here we can ensure that both news article and tweet contain summary by implementing the trait summary for news article and implementing the trait summary for tweet. Notice how we define summarize the same as it is defined here for both of them. Now, since we defined it for both, we can use the .summarize function the same way, essentially. So traits, as mentioned earlier, can be used to specify what type of data type we're accepting, what type of generic. It can filter down. Like for example here, this notify only accepts any data type that implements the trait summary. Like for example, this would accept the news article or tweet that we defined earlier where we implemented summary. Here, we have an example of how you can specify multiple traits implemented in a type. Use the plus syntax. So you implement this and you implement that. See how first here we clone it and then we summarize it. It means T must have both summary and clone implemented. There's also another syntax we can use with this, which is the where syntax. This is a bit more clunky though. You might not find this as much. This is quite clean. So trait bounds can be specified anywhere it appears. For example, T here can be for clone and display, but not summary. Here it's clone, display, and summary. Yeah. Some methods can be provided to you without having to define it yourself. For example, we have summary here, which isn't summarize here, which isn't defined. So you need to define it when you implement it here. When you implement summary for tweet. But self-notify, as we'll notice, has a default definition already provided for you. So you don't have to define it every time you implement summary for a struct. For example, here, this self-notify only calls summarize and would do the exact same functionality when you call it here, when you call it from a tweet. So the motivating example that we covered last time is this comparison. You have an at type here and an at type here, but you want to restrict it to only types that can be compared using a greater than symbol. This means that we need to implement the standard compare partial order trait. This trait implements all the comparisons we need. As we did earlier, integer, a 32-bit int, and character both implement the partial order in themselves, so they would work. But since it's a generic, we're not sure yet if it implements it. So just as mentioned here, we can call this. So first, some information on these specifically. Partial EQ and partial order are two default traits in Rust that are very useful when defining your own data types. Partial EQ defines the equal and not equal operators. This is very easy since not equal is defined for you. It just returns not times whatever equal returns since it's a Boolean. So you just need to define equals. See here how it ends in a semicolon and not a function definition. Partial order is a bit more expansive. It builds off of a partial compare, which already defines these things, but it also defines that, okay, I'm not sure if that's correct, but it already defines less than and greater than, this trait defines less than and greater than for you, which you can implement under this interface here. Since it already uses from partial comparison, these two, they already have provided methods here. So you just need to define partial compare. You just need to define its ability to define these. Once it understands these, it can build these from it. And partial EQ is used to verify that you've defined this correctly. Once you implement all of these, by implementing partial CMP, your data type is now comparable. Like for example, if you inherit the comparable class in Java, if you've taken Java before. So this is an example of how we can fix our function from earlier. We can specify that the generic T must implement the partial order trait, which means that it implements this greater than sign. So it's comparable. So here are some more common traits you may encounter. Display. This allows it so you can use the println function with the open close brace notation. For the open close brace with colon question mark, that's the debug trait. From string allows you to convert from a string to your data type. So for example, if you have in quotes the number 1, you'd be able to convert that to an integer. Clone allows you, in capital C, allows you to clone a value using the .clone method. This is useful if you want to duplicate values without violating the laws of ownership and borrowing. Default allows you to set a default value for type. Like if you don't specify it, it'll set itself to this value. Borrow, as mentioned, lets you borrow it. A hash allows it so you can use your data type in a hash map as a key or in a hash set as an element. Then some more. Into iterator allows you to iterate over it, like into iter, or like iter and iter mute, which we covered in previous lectures. And the loop in Rust is also tied into the into iterator. Fun fact. So, to implement some of these, often you can use the derive, the hashtag open brackets derive notation here, where it tries to derive all of these traits in here. The derive works if all of the fields in a struct already implement these traits. Like for example, X, it's already comparable since it's an I32. So it already implements both of these traits. So now point can implement it too, since partial order here is already implemented for all the subfields. So it'll just compare it for the subfields between the two. If you have different second members or first members, it'll take priority of the first member first. Like for example, in this example, point 1 is less than point 2, even though y1 is greater than y2. It's because x1 is less than x2. So, thank you for listening. Another announcement is homework 9 is now released, and it'll be due next Wednesday at 11:59 p.m. Thank you for listening.